At this point, we've got a bunch of propositional operators that we've considered, and we use them to form propositional expressions. And we know for any such propositional expression or propositional formula how to get a truth table for it. But it's useful to know that every propositional formula has a special form that we can put it in that's convenient, called a normal form. And as a matter of fact, by showing how to get a formula into normal form, we actually wind up with a stronger conclusion. We've already seen how you give me a propositional formula and I can evaluate it, all the different truth assignments, and in that way fill in the rows of a truth table for it. But what about conversely? If I gave you the truth table, would you know how to find a propositional formula that had that truth table? Well, maybe you could figure that out, but I'm going to show you now a way to read such a special form propositional formula, a normal form formula, right off the truth table. So, in fact, there is this special sum of products formula that we're going to aim for first. So by a sum of products formula, I really mean an OR of ANDs. So, and we'll see a concrete example of that very soon, because I'm going to do an example. This is called a disjunctive normal form. Disjunctive means or. So you're taking a bunch of terms that are ands of things, and then you're oring those ands together. That's a disjunctive normal form, or DNF for short. Okay, let's do an example. Majority function is kind of fun to work with because it has an easy top-level description. In this case, it's the majority function on three variables, P, Q, and R, and it's true precisely when most of the variables are true. So if 2 out of 3 of the variables, or all 3 of the variables are true, M of those variables is true, and you can see it in 1, 2, 3, 4 rows where it's true and 4 rows where it's false. Those are the rows where there are more falses than trues. Okay, let's look at a particular row where the majority function happens to be true, namely in the row where P is true, Q is true, and R is false, the TTF row. And we've singled that out because that's a row where M has the value T. Now, the way I'm going to find the formula that corresponds to this truth table is by making an observation that there's a simple term, P and Q and not R, and this term has the property that it's true precisely when P is true and Q is true and R is false. It's an and, so the only way this and term can be true is when each of the individual variables gets a truth assignment that makes it true, which means it has to be P is true, Q is true, and R has to be false because it's getting complemented. And that's going to be the only place that it's true, and it will be true there. Okay. This kind of a term is called an AND of literals. A literal is either a variable or the complement of a variable. R bar is the complement of a variable. Q and P are just isolated variables. So an AND of literals is when I have a product of literals, an AND of literals. So let's give this a name. I'll call it A super TTF. For the AND at the row TTF. And I remind you that ATTF has the property that it's an AND of literals formula that's true exactly in the row or under the assignment TTF, and it's false under all other truth assignments. So now it's easy to get this disjunctive normal form for M that I want, because M is true in 4 rows, in 4 truth assignments, where the ones where there are more T's than F's. These are the 4. And so if I take the AND of literals terms for each of those assignments that makes M true, namely ATTT and ATTF and ATFT and AFTT, and I OR them together, what I get is a formula that is going to be true in exactly these 4 rows. Only these 4 truth assignments make it true. Let's check that. If I looked at the truth assignment all trues, then ATTT is true, and this is an OR, so as long as one of them is true, it's true. Likewise, the A super other assignments contribute a true when you use that assignment, so it makes the whole OR term true. And those are the only ways that these 4 terms are true. If it's not one of these 4 truth assignments, then all 4 of these ANDs of literals are false, so this whole OR is false. In other words, again, this formula, the OR of the AND of literals terms corresponding to the true rows, has the same truth table as M. It's a formula for M. There it is spelled out. So this is a disjunctive normal form formula. For M, disjunctive normal form means it's an OR of individual terms that are ANDs of literals. An AND of literals technically is a term that's got at most one occurrence of each variable. So it won't have a Q and a Q. It won't have a Q and a not Q. So each of these has the variables at most once. As a matter of fact, these special ones that we got are even better. They not only have each variable in the AND term at most once, they have it exactly once. So each product has all the variables, and that's what makes it a so-called full DNF for M. So a corollary then is that every formula is equivalent to a full DNF. I illustrated it for the majority function M, but the same method applies whatever function you're dealing with. Every formula is equivalent to a full DNF because you just read the full DNF right off the true rows of the truth table for the formula that you're trying to re-express as a full DNF. Or if you've just given the truth table, you can find a full DNF formula for which that is the truth table. So you just read it right off the true rows, and the formula really, in a certain sense, looks like the truth table. It's just a listing of the true rows. In particular, this means that if I have two formulas that are equivalent, remember equivalent means that they have the same truth table. Well, if they have the same truth table, then they're going to wind up with the same full DNF formula. So if two formulas are equivalent, then they are actually equivalent to the same full DNF formula. Where same, I need to hand wave a little bit because I got to alphabetize or sort the terms in the full DNF. Remember, an AND of PQR is the same as PRQ because I could list the literals in an AND clause in any order and they'll be equivalent. And likewise, I could take the AND of literals terms and they're just ORed together, so I could list them in any order and it won't be the same term if I shuffle them in different ways. But if I alphabetize everything, that will force the full DNF to be unique. And in that case, I can say that every formula has a unique sorted full DNF that is equivalent to it. Okay, next case is sort of the dual of sum of products, which is where we look at a product of sums. And what I'm now going to do is repeat exactly what we did for sum of products, but using product of sums, where basically ands and ors get reversed, and the same logic, and trues and false actually get switched, but the same logic applies. So if you understood the first part of this short video, you could skip what I'm about to do, but what I'm about to do is a easy enough short review. So let's do it. And I'm interested in an and of ors, a product of sums, and this is called a conjunctive normal form. A conjunct is one of the terms of an and. So CNF is what we're aiming for now. So let's look at the majority function M again, but this time I'm going to look at a false row. So the majority function is false in the row TFF, for example. There are three other rows where it's also false, but let's focus on the TFF row, and where we have this value F. And now, instead of taking an and of literals, I'm going to take a term, the term not P or Q or R. So I'm looking at TFF, but I'm taking the complement of P and the uncomplemented version of Q and R corresponding to the F. And why did I do that? This or term has the property that it's false exactly in this TFF assignment. That is, in order for this or to be false, all three of the terms have to be false. If any one of them was true, the whole thing would be true. So that means that it's forcing not P to be false, which means P is true, and it's forcing or to be false, which means it's forcing Q to be false. So Q is false and R is false. And this then is a term that's false exactly in this row or under this assignment. Only in all other truth assignments for the three variables, it comes out true. So this is an or of literals term corresponding to and of literals in the previous example. And we'll call it DTFF for disjunction of literals or of literals, DTFF. And again, this has the property that it's false only under the assignment TFF. It's false only in row TFF. In all other rows, it's true. Okay, so now if I look at the rows where the majority function is false, there are four of them, and I take the or of literals for those four terms, I wind up with this formula, which is an and of the 4 ors of literals. And the claim is that this is false exactly in those rows. Why? Well, if you're in one of the rows, say FFT, then this DFFT term is false, so the whole and is false. But if you're not in one of those rows, then every one of those D's is true, so the whole and is true. So in short, this simple way of forming an or of and of ors formula is one that is going to is going to be equivalent to M, and it's a conjunctive normal form. Here it is spelled out. So you're anding together these 4 or terms corresponding to the 4 rows. And again, each of these or terms has one occurrence of each variable. So since it has all the variables, this format of formula is called a full CNF. And by the same reasoning now, we've just concluded that every formula is equivalent to a full CNF because you can just read the CNF right off the truth table of the formula. And again, if 2 formulas are equivalent, then they have the same truth table, and therefore they will be equivalent to the same full conjunctive normal form, again with the little proviso that I have to sort in order to make the format of the formula unique.